Okay, in this video we're going to talk about centers of triangles. And believe it or not, there's actually thousands of centers of triangles, but we're only going to learn 4. So let's just draw a triangle, and I'll tell you what I'm talking about. So let's say we come down here, and here, and here. Notice where they intersect. That would be a center. But there's more than one type of center of a triangle. For example, if I drew medians, and a median is when you come from, one vertex and you come to the opposite side and you cut that in half. So it's like a bisector of the opposite side. So let's read a definition. It says a segment from a vertex to the midpoint of the opposite side. So medians always cut the opposite side in 2 equal parts. And we need to define concurrency. Concurrency is when 3 or more lines, rays, or segments intersect at the same point. They're called concurrent lines, which is what's going to happen. Every time we have a center of a triangle, there's going to be 3 lines intersecting. So that's why it matters. It's 3 or more. And so this is going to qualify. So all of these are going to be concurrency or concurrent lines or lines of concurrency. When you have a median of each side and the 3 of them intersect in a point, it's called the centroid. So notice that each of these is a median. And the way you can tell that is because it comes from the vertex and when it gets to the other side, it breaks it into 2 equal parts. And all of them do that. So there's this one, and then if I start over here, I got this one, and you can tell that they're medians because no other, well, it's not completely true, but it's not perpendicular, and it doesn't have any other markings except for the fact that it's a bisector. Okay, so again, we have the medians, which is a centroid, and it actually has mathematical properties, like numeric things that we can use. And what happens is that the distance between the vertex all the way until it gets to the center is 2/3 of the distance. And then from the centroid to the outside edge is another third. And they're all like that. There's a couple different ways that you can use that information to solve. I think if you leave it as fractions, it's actually going to be harder. So let's just talk about the fact that, let's say, from A to B, and then C. So from A to B, it's 2/3, and from B to C, it's 1/3. The best way to think about this is a ratio. There's 2 to 1. And whenever you're dealing with a ratio like this, when you set it up as an algebraic expression, you add x's, okay? So you got 2x and 1x. And another thing that you do is you say 2x plus 1x would equal the whole thing. So let's say AC was 30. Then each part would have to be 10. So this would be 2 10s, which would be 20, and this would be 1 10, which is 10. So let's just do an example, and hopefully it'll make sense. So it tells us that P is the centroid of this triangle, and that EP is 8. And then it wants to know what PC is, and what the whole thing EC is. So what we're going to do is, you have to think about, is this the 1/3? Or is this the 2/3? Well, it's the 1/3, okay, because it's not coming from the vertex. The vertex to the centroid is 2/3. And then from the centroid to the edge of the triangle is the remaining third. So here's what we know. We have a ratio of 2 to 1. And so that's like 2x to 1x. But they tell us the 1/3 part. They actually say this is 8. So x is 8. That's really what we know. 1x is 8. So 2 x's would be 16. And then all together they would have to equal 24. So EC, the measure of EC would be 24, and the measure of PC is 16. So what you really have to ask yourself, every time you do a centroid problem, you're going to have like 2 to 1, okay? Either they're going to give you the 2/3 part, they're going to give you the 1/3 part, or they're going to give you the total. So if they give you the 2/3 part, you're going to do 2x equals that number. If they give you the 1/3 part, you're going to do 1x equals that number and solve that. If they give you the total number, like the total length of both parts, 1/3 and 2/3, then you're going to do 3x equals that number and solve for that. And that's really what you're going to do every time. And the best way to think about it is algebraic, just like you would ratios. Okay, so let's go ahead and try to do some examples like this. It asks us to find BC, CD, and AY. And they're talking about the length of each of those. So we're going to have numeric values here. Let's start with AY, which is this one right here. And they give us, you can tell by looking at it that they give us the 1/3 part. So don't forget, if it was, 2, this would be 2x equals something, 1x equals something, or if they gave us the total length, it would be 3x equals something. So they gave us the 1/3 part, so what we know right now is that x equals 6. And what we also know is that the other side is 2 x's, which is 2 6's, which will be 12. And now that we know what each of the parts are, we can add them together, and it'll be 18, because 6 plus 12 is 18. So I'm going to write it down here, AY equals 18. And I'm going to erase and get started on the next one. So let's do BC next. Well, it doesn't matter. Alright, we'll just do CD. Okay, CD is this one right here. And once again, they gave us the 1x, because you can tell it's only 1/3 of the distance here. And so that means x equals 10. And 2x would equal, 2 x's would equal 20. So that means this is 20. And they're asking us for the length. That's it. So CD is 20. Because they're not asking us for the entire thing. That would be CX. So CD is 20. Now BC is a little different, because BC is talking about a median. Notice that the only way that this would be a centroid is if it were a median, which means that AY is going to come down here and cut this side in half. So if this is 20, so is this 20. And the only way we know that is because of the median, what the definition of a median is. So BC would be the whole thing, which would be 40, because 20 plus 20 is 40. So there's a lot of applications that you need to be able to use, and it's hard to remember everything. But if you practice enough, it'll come back better. So we're going to do a lot of practice problems. Okay, the next thing we're going to go over is altitude. You might already know what an altitude is because of area in middle school. But altitudes are when in a shape, let's draw a shape here, it comes from the top and comes down at a 90-degree angle. And it could be inside the triangle or the shape, or it could be outside. Like an obtuse triangle, their altitude would be outside, because that's where the tallest part of the triangle is, and to come straight down, you don't actually come straight down inside the triangle. So altitudes could be inside the triangle or outside the triangle, or shape for that matter, any of the shapes. Trapezoids have altitudes, parallelograms have altitudes, and so forth. So think about altitudes as being the true height of the shape. Like, it's not the slant height, it's not this height. It's the true height, up and down, vertical. So if somebody were measuring you, you wouldn't lean over and then let them measure you, because then you wouldn't be as tall as you normally are. You'd be, a different height. Okay, so let's read the right-hand side first. It says the altitude is the perpendicular segment from a vertex to a line that contains the opposite side. All acute triangles have, they meet inside the triangle like this, okay? Acute triangles their altitudes will meet inside the triangle. Right triangles, the altitudes actually meet along the edge, like it's on the side, which will be right here in this one, because this is an altitude because it's straight up and down, and this is an altitude because it's straight up and down if you turn the triangle the other way. And the only one that actually has what we would consider a true altitude, where you can see it, is this one, but they all three meet in that corner. So the altitude of right triangles is actually, it lays on the edge of the triangle, not inside. Obtuse triangles, two of the altitudes are on the outside of the triangle, and then one of them is on the inside. So that's why I really want you, let's go back. Notice that it says a perpendicular segment from the vertex to the line that contains the opposite side. Normally they would say to the opposite side, but it might not be actually on that opposite side. I'll show you what. Okay. So this altitude would come down here, and it would exist out here. But it's actually not laying on this line segment. But if the line were to be extended, then it would. And that's why it says the altitude that it's a perpendicular segment up to the line that contains the opposite side. Because if you would extend this, then it would be there. Okay, so when all three of the altitudes actually do intersect, whether it's inside the triangle, outside the triangle, or on the triangle, it's called an orthocenter. Orthocenter, that's hard to say. But that's the second center. So we've gone over centroid, and we've gone over orthocenter. There's two left. Okay, we've gone over medians and altitudes. There's two left, and one of them is perpendicular bisectors. So if I came across here and bisected this with a perpendicular, and I did the same over here, let's say it was like this. Well, let me redo that. So it's this. Again, I did the same over here with perpendicular bisectors. Then that would be called the circumcenter. That point of concurrency is called the circumcenter. And the reason they call it the circumcenter is because if you were to draw a circle on the outside and connect all three of the vertexes out here, this one's a little bit further out, but in theory, this would be the radius here, and this would be the radius here, and this would be the radius here. So it's like as if you drew a circle around the triangle on the outside edge. And I think that it's easier to remember like that because circumcenter sounds a lot like circumference, and circumference is the distance around a circle. So perpendicular bisectors, when they connect, when they intersect, they create a point called circumcenter. The last type of center that we're going to talk about is when you cut the angle in half. So it creates two, like an angle bisector. And then I cut this one in half, and then this one in half. And when they intersect, angle bisectors intersect, then it's called an incenter. And the interesting thing about an incenter is if I were to draw a circle inside the triangle, then each of these is a radius of the inside circle. And I think it's actually easy to remember that one too, because that one creates, it's called incenter, and it creates an inscribed circle. Okay, so we've gone over all four types, and there's I guess a cheat sheet, if you want to call it that, in your packet, and it looks like this. What we need to do now is we need to come back through and really just try to memorize, because it's very hard. They all feel very similar, and it's hard to know which is which, especially if you're not looking at this paper. The one thing that I remember memorizing when I was younger was the altitudes and the orthocenter. And I had braces when I was younger, and I had to go to the orthodontist. And I always said that altitude sounded like attitude, and I probably had attitude when I went to the orthodontist. So attitude and orthodontist versus altitude and orthocenter. So I was able to memorize those that way. But you still have to know what altitudes are and be able to draw them, which is the hard part. And not all the altitudes are on the inside of the triangle. So you can see in an acute, let me move this down, in acute triangles, they're on the inside. In right triangles, they're right on the triangle themselves right here. And in an obtuse, it's on the outside of the triangle. So those are things that you're just going to have to either try to figure out or memorize or do something. It's not like you're going to get asked a ton of questions about these, but still, it's a good method to try to memorize as much as you can, because you never know when it's going to be useful. Geometry is really bad on just expecting you to know everything you've ever been taught and not reminding you of it. The next one that I think is kind of, well, none of them actually have anything to memorize anymore. We're going to have to make something up. I think that I would try to do, and I know it's far-fetched, but centroid to me reminds me of space, like a meteoroid. So I think I would do medians as in aliens. So median is an alien, and centroid is like outer space, meteoroid. I think I would be able to remember that. If you don't need help memorizing it, that's fine. I'm just trying to help you out. And circumcenter has to do with perpendicular bisectors, and the incenter has to do with angle bisectors. So you'll have to come up with something P for circumcenter and A for incenter.